Thank you for the introduction, and bonjour. So, to start with, 3D whole art MR angiography has shown significant potential to visualize the coronary arteries, but it still requires a long acquisition time to obtain highly resolved isotropic images. Under sample acquisition, using compensated reconstruction can accelerate CMRA, but for high acceleration factors, it suffers from residual aliasing artifacts, high computational cost, and high dependence on regularization parameters. Variational neural networks have been previously proposed to overcome this limitation, but only for 2D static images of the knee. The purpose of this work is to use a multi-scale variational neural network to allow for fast reconstruction of 3D high-resolution images from prospectively undersampled translational motion-corrected CMRA data. As you saw before, we use a 3D variable density under sample trajectory with Cartesian-like spiral profile ordering. And to correct for motion, we use 2D image navigators, but precede the acquisition of each spiral arm to enable bit-to-bit 2D translational respiratory motion correction. The multiscale variational neural network is an unrolled network and an end-to-end network. And each stage of the network sees as an input the case-space data, the color sensitivity maps, and it gets as an output 3D CMRA images. Each stage of the network can be seen as a gradient step of a conventional iterative reconstruction algorithm, which has data consistency term with respect to the undersample case-space data on the top, and the learn regularization term on the bottom. For the regularization term, we learn in parallel magnitude images and phase images. And for the magnitude images, we use a multi-scale approach, where filter kernels and variational activation function are learned. We acquired 18 LT subjects on a 1.5 Tesla, using an ECG-triggered 3D BSSP sequence. And we used 10 subjects for training, using fully sampled images were 5-fold and 9-fold retrospectively undersampled in order to ensure that the effect of respiratory and cardiac motion in both input and target image was identical. The remaining 8 subjects were used for evaluation of the reconstruction and were prospectively 5-fold and 9-fold undersampled. The network was trained on 2D images, and so 2,400 images were used for training and 320 for testing. And all the construction parameters were learned offline, including the lambda term. On the right, I show intermediate outputs for magnitude image and phase image. And on the bottom, you can see the difference between the intermediate outputs and the input of the network. As you can see, the magnitude images, the network learns some features like texture or edges for the magnitude images, whereas the phase experiences a smoother transition. Here we show examples of learned parameters of the multiscale VNN for the magnitude on the left and for the phase on the right. In blue, you see the activation function, and in red, the potential function. You can see how, for example, here, the potential function can look like an L1 norm function, which you use in comprehend sensing, whereas, for example, some of those, they might look like T-student functions, which are associated with sharpening. Whereas for the phase, you see that all the activation functions are linear and the potential functions are convex as we, again, experience a smooth transition. Here I show results for a representative LT subject for 5-fold acceleration, and for zero field on the zero field reconstruction on the left, comprehensive reconstruction, and the multiscale variational neural network in comparison to a fully sample acquisition, which is acquired in a consecutive but different scan. On the bottom, I show the reformatted images with respect to the left and right coronary arteries. And when I show a second representative LT subject for 5-fold acceleration, and you can see how the results of the multiscale variational neural network are very similar to the fully sample acquisition. And the fully sample acquisition was 18 minutes long, and 4 minutes for 5-fold acceleration. The reconstruction time was 5 minutes for compressed sensing and 14 seconds for the variational framework. Here I show results for 9-fold acceleration for a third healthy subject, and here for a fourth acceleration with fourth healthy subject with 9-fold acceleration. And again, the fully sample acquisition was 19 minutes, and the 9-fold accelerated acquisition was 2 minutes 30 seconds. The reconstruction time of the variational network is still 14 seconds. I show also some quantitative results in terms of vessel sharpness for the right coronary and the left anterior descending artery, and for 5-fold and 9-fold acceleration, and quantitative results also for vessel length. So both sharpness and length show that our reconstruction is the quantitative results are very similar to the fully sample acquisition. In order to demonstrate also the generability of the network to multi-contrast imaging, I show some example quickly, some preliminary results with MTC Boost. MTC Boost is an interleaved acquisition where we acquire a bright blood image for anatomical visualization of artery and veins, and a reference image which, with the speed reconstruction we can obtain a black blood volume. I here show results with the multiscale variational neural network, in which we learn in parallel the bright and the black blood image. And you can see again how the variational for 5-fold acceleration. So we can see how again we obtain very good image quality, very similar to the fully sample acquisition for bright and black blood. The acquisition in this case was 12 minutes for fully sample, and between 2 and 3 minutes for the 5-fold acceleration. The reconstruction time was 10 minutes for compressed sensing and 20 seconds for the multiscale variational network. In conclusion, free breathing, motion compensated whole arc 3D CMRA with 1.2 mm isotropic resolution was successfully acquired in 2 to 4 minutes and reconstructed in 14 seconds using a multiscale variational network, which enables improved CMRA, reconstructed image quality, short scan times, no need for tuning of regularization parameter, an extremely fast computational time, and also can offer generalization to different contrasts, as for example, bright and black blood. I thank you for listening, and I thank also my collaborators at King's College.